This is Nanoscape. I'm Seth Zimmerman.
And I'm Erin Spain.
On this show, we venture into the frontier of nanotechnology
With experts in the field who are turning the science of small into the next industrial revolution.
This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University.
Today's guest, Professor Ted Sargent, is redefining what's possible in clean energy research by advancing the field of solar energy harvesting, lowering its cost and increasing its efficiency by using nanoscale materials.
Ted is a global leader in nanoscience and materials engineering, and his work also includes decarbonizing the chemicals and fuel sectors and creating new materials for consumer electronics, such as those that can assist in new infrared sensors for smartphones and self-driving cars.
Here at Northwestern University, he is the Lynn, Hopton Davis, and Greg Davis Professor of Chemistry, Electrical, and Computer Engineering, and the Executive Director of the Trienens Institute for Sustainability and Energy. We are delighted to have him on the show today to talk about his groundbreaking research in nanoscience. Welcome to the show.
Thanks for having me.
Your group is called the Sargent Group, while Sergeant Pepper's Nano Hearts Club Lab sits collecting dust out there. What happened? Where did we miss this?
Yeah, I guess we've been that for a little while now. Maybe we could work on a more original name. Maybe you guys can help us out.
Yeah. We'll spitball some fun new names
Yeah.
for the group. Love that.
Put a poll out for everyone, see what they think. These days, your name is a mainstay on annual highly cited researchers lists, but take us back to the beginning of the career. What moment or idea or mentor really set you on this path towards nanoscience?
I'd been working in the early parts of my career, both my PhD and then when I was an early career faculty member, on making lasers out of very thin layers of semiconductors. These are called quantum well lasers. And I got really interested in some work that was happening right around that time. We're now in the early 2000s, maybe 2001, 2, 3, based on what are called colloidal quantum dots. So these are also semiconductors. They're also small. They're also nanoscale, but they were being made as liquids. And what was exciting was that you could coat them on kind of anything. So you could put them on another semiconductor. There were no problems there. You could even put them on roll-to-roll plastics. So you could think about doing flexible electronics with them. But the thing that wasn't solved is, how do they actually work in devices? Like, how do you actually get light out of them, or how do you get light into them? How do you get electrons in and out of them? And so I became really interested in using my skills in semiconductors, but applying them to these new nanomaterials.
Your work on perovskite solar cells is a promising alternative to these traditional silicon solar panels that we all know right now. And these are really revolutionizing solar technology. Explain these cells to me and how you got started with this and how your group is using and improving them in the lab to really now push the limits of solar energy.
Yeah, it's incredible what's been accomplished with silicon solar cells. They're dominating the industry today. And when you see a solar farm or when you see something on somebody's rooftop, you're looking at silicon solar cells. So it's been an incredible generation and an incredible run. And then the community, especially the upstream research community, like people in universities, are asking the question, what next? How could we do even better and build on the achievements of that sector? And I think the answer always comes down to, how could we make things even more efficient? So for a given area of solar cell, for a square meter of solar cell, how could we produce even more electrical power? And this means we'll make better use of the area of your roof or of your solar farm. And it also means if it costs us a certain amount of money to install a square meter of solar cell, we'll yield more electricity for that dollar of investment. And so this is the route to further decreasing the cost of solar electricity. So where the perovskites come in is that these are very versatile materials. These are materials that can be tuned to absorb different colors of the sun's broad spectrum. And as a result of that, they can ultimately make solar more efficient than what we can do with silicon.
So where do things stand right now with some of these projects? I mean, I actually just did a quick Google search and I saw some people were wearing vests with those cells on them. And they were like, maybe we could, charge our cell phones with these solar vests. I mean, tell me about some of the different applications that are being tried out there.
I think the big one that everybody still really concentrates most of their energy onto is the one where we're really meeting the growing electricity demand that we face today. And so that's actually the big applications. That's the big solar farms and rooftop, but often like industrial rooftop and things. And so I think that's what everybody's putting most of their energy and their focus into, because that's where we really get to decarbonize the electricity supply. And that's how we're going to make a big impact in a world where electricity demand is growing. I mean, just look at AI and data centers and growth there. There's a lot of additional electricity demand we're going to have to fulfill including over the coming 5 and 10 years, and minimizing the carbon impacts, the carbon intensity of meeting that additional demand for electricity is a really important global priority.
And you've said obviously efficiency and costs are incredibly important for new energy, but so is durability. And so, what are the biggest stability challenges that you're kind of trying to tackle?
For the last 5 years or so, the perovskite solar cell community has turned its attention to this durability challenge. About 5 years ago, there were some super exciting results on performance, power conversion efficiency, but often the solar cells were kind of fragile. And the efficiencies raised excitement, but the durability issue raised alarm or skepticism. And so, really, the community had to go tackle it. So, we've certainly been part of that effort. And the great news is that over the last 5 years or so, the field has really matured these technologies very considerably. And so, the way the field judges durability is it applies higher and higher temperatures to the solar cells, actually a lot higher than they'll actually ever see, even on a hot day in the sun. It's called accelerated lifetime testing. And it's the way in which we learn quickly about whether a solar cell is really robust or whether it's not. And these solar cells that are now using the industry standard and the most demanding lifetime tests are now surviving for thousands of hours under those demanding tests. Now, if you do the math, that's still not enough to have something 25, 30 years in the field, but it's a step in the right direction. And the community continues to now study durability science, continue to improve performance, and invest in making these truly robust and also deeply understood.
Is it in the world out there at this point? Or are we still kind of in the lab figuring things out before we really start rolling it out?
Yeah, there's some work to start scaling and to start deploying. So there's some companies that are moving ahead, which is really exciting. They're starting to get some field testing done. There's also just a growth even within kind of the research community for not just doing testing inside the lab where you can control the temperature and the sunlight and things, but for literally going into the field and going up on a mountaintop and testing your solar cells under the most literal real world conditions that you can have, and to try to see whether what we do in the lab with our standard test, does it actually at least correlate? Like, can we make the connection between what happens in the lab and what happens in the field? This is a really important new milestone in the field.
Let's turn our attention to another focus of your work, which is converting CO2 into useful fuels and chemicals. Talk to me about that and where that work stands right now, how close we are to seeing this technology make a real world impact.
Being able to take carbon dioxide, and there's a lot of it today, there's a lot of it that's being emitted, being able to take that and turn it back, kind of create circularity, turn it back into a material or turn it back into a fuel is a really important priority area. So our approach has been to find how to use electricity to power that process. So you can imagine from solar and wind and from nuclear, there's a lot of electricity that's being produced, and we need a whole lot more in the future. Some of that can be allocated towards making carbon dioxide back into a fuel. And because you consume as much carbon dioxide in making the fuel as will be emitted, it becomes, you call it a sustainable fuel, or you can talk about kind of closing the carbon cycle or closing the carbon loop. Now, the biggest challenge for this field, and it's the one that we focus on, is to maximize that energy efficiency. I mean, there's some energy requirement that you can't get away from. Intrinsically, there's more energy content in a fuel than there is in carbon dioxide. And so you're going to have to pay that energy no matter what. The question is, how much do you have to pay on top of that energy? And so when you get an energy efficiency that's as high as possible, you come as close as possible to that minimum energy input. And that's really the focal area for that topic, which is designing catalysts and designing systems that achieve the maximum energy efficiency.
We're going to talk also about general consumer electronics. So you're working on materials that could one day power lighter, faster, more efficient devices. So Give us a glimpse. What's tomorrow's electronics going to look like?
Well, one of the things that I'm really excited about in electronics and optoelectronics is in making better and better sensors for light. There's cameras everywhere. You got multiple cameras in your phone and in your car, and it's a big industry. It's grown into a multi-billion dollar sector if you even just look at the chips that underlie that sector. So it's really grown, and it's also had a huge amount of impact. Just imagine, how our lives have changed thanks to having cameras everywhere all the time, always with us, connected. So it's very exciting. At the same time, there's some new frontier areas for light sensing, and one of those is to get further and further into the infrared. When we look at longer wavelengths, we can see farther into the distance with LiDAR in our cars, and so we can make safer self-driving cars down the road. We can also see information. We can actually see chemical information in the atmosphere with certain wavelengths, and so we can learn about whether there's like a cloud of methane that's being emitted somewhere. But we do need sensors that are capable of seeing these wavelengths, and the existing silicon sensors don't do that. So our work is with colloidal quantum dots, so these semiconductor particles that you can tune through the quantum size effect to make nanomaterials that can see these wavelengths that are otherwise invisible.
So this is happening in your lab right now. You have students. Give us a little status update on what's happening in your lab with that work right now.
Yeah, it's really exciting. The team's doing great work, and one of the amazing things about being in Northwestern is the ability to go end to end. We've got incredible PhD students and postdoctoral fellows who are synthesizing these new materials. So they come from the materials chemistry field. We've got others that are studying what's going on the surfaces of these materials. Often they use light. It's called photophysics or ultrafast spectroscopy. They use light to study what's going on inside these semiconductors. And then we've got materials processing experts who kind of take one of these synthesized sets of quantum dots and make a material out of them. They make a film that you can coat onto a substrate. And then we've got the device physicists and the device engineers who are working all collaboratively to study how light is absorbed and how electrons and holes move around inside these semiconductors. So Northwestern actually has multiple superpowers, but one of those superpowers is interdisciplinarity, and the fact that you can build great teams and you can connect great teams and you can work with great colleagues on these really important problems that really require teams with a lot of diverse expertise to work very actively with each other.
And then Northwestern also many times can help you bring these new discoveries to the marketplace. And this is something that you have experience in. You have co-founded several startup companies. One was actually acquired by Apple in 2017. Tell us about this part of your work and why it's so important to help bring these new discoveries to the marketplace through startups.
Yeah, one of the really exciting things about working in this field is that, as well as there being some really exciting and important basic science and some discovery, is also it has the potential to impact people's lives, to impact, the environment, to impact feels like consumer electronics that we all benefit from. And so one of the awesome things about being at Northwestern is that there's this tremendous history of spinning out companies. There's a great history of entrepreneurship, and there's also great history of collaborating with companies. So there's great companies in Chicagoland, in the US and around the world that have a strong appetite to work with researchers at Northwestern. And so we can have impact through both of those mechanisms, right? Some technologies were meant to be spun out and venture invested in and a company built, and others are probably more set up for real impact on climate, on the economy through partnerships with industry. And at Northwestern, we do both.
Let's talk about artificial intelligence for a minute. Artificial intelligence is becoming just a massive new tool in the research tool belt. So, how is AI and machine learning really changing the way that we search for and design new materials at the nanoscale?
I see the potential impact of AI as being in a position to allow us to move faster. And so the problems we work on are so urgent, right? When you think of the climate, when you think of sustainability, when you think of the need for more energy, when you think of the need to enable people to be better connected and to communicate with each other, these are so important and they're time sensitive. We need to tackle these problems today. And so if we can speed up the process of discovery, then we can have impact faster. And so the way I see AI coming in is in a couple of ways. One is if we can use machine learning to learn more quickly the guidelines about how a material, how you synthesize it, what its properties are, how that material can then function inside a real device like a solar cell or a catalytic system, then we can move more quickly. And ultimately, we can move more quickly towards impact. One of the exciting areas for that is to kind of fuse information that we get and learn off of information we get from computation. We have great computational material science, including at Northwestern, and also off of data. We're getting more and more data. So, for example, Professor Chad Merkins developed a really transformative approach to high throughput synthesis and study of materials called mega libraries. And then if we get both the computational data and the experimental data from Chad and his team, I think we'll be able to learn more accurately and ultimately direct our efforts more swiftly towards these kind of impacts.
In your lab specifically, how have you started utilizing, or any of your postdocs or PhDs really finding, an example of how exactly they're using AI machine learning like yesterday?
Yeah, so one of the applications of AI that I'm really excited about is in discovering new catalysts. And so, specifically, one of the big opportunities for the future is to find ways to make hydrogen using electricity and water in a more energy efficient way. And here, the biggest cost of the hydrogen is the electricity. And so, if you can make the energy efficiency higher, you can reduce the cost of its production. And the biggest gating factor in having more hydrogen being used is to decrease its cost of production. And so that's a really key priority for the field. So we've been working to try to discover new catalysts that are particularly good at producing hydrogen with the lowest possible overpotential. So the overpotential is the extra voltage that you pay to make hydrogen beyond what thermodynamics requires. So it's this sort of extra penalty or tax on top of the value of what you're really making. And when we think of designing these new materials, we actually look quite broadly across the periodic table. And the periodic table's already got a lot of elements on it, but you can combine them in pairs or in triplicates or in quadruplets. And all of a sudden, you have billions of possible materials that you could be surveying. So one of the great things about the AI that's informed by both computational work and also by experimental data is that we can move more swiftly through the periodic table and find new catalysts that are both efficient and stable.
So you're talking about, this computational data that is happening, but your lab itself is truly a cutting edge space. When you came here to Northwestern, you were able to sort of redesign this lab with all the infrastructure needed to enable these breakthroughs. Can you just talk to me a little bit about when you bring someone through on a tour of your lab, you have like these sealed glove boxes, humidity control, real time device monitoring. Talk to me about this incredible space and what it means to have, all these tools at your disposal to do the work.
Yeah, one of the amazing things for me about the opportunity to join Northwestern was to really build a lab from scratch and to build it for exactly the kind of work that we do. We really needed to have very excellent control over things like the humidity of the lab, the temperature in the lab, the environment in the lab, even like the workflows and how the students and postdocs move around, how they collaborate with each other. And so we were able to design all of this kind of from scratch, from first principles in partnership with the design team at Northwestern. And as a result, we have the full flow. We can go to end from making new nanomaterials to making them into actual solid materials that we can study, we can investigate, from the lasers that allow us to ask questions about what's going on in the surfaces or inside these materials, and then to also making record-setting devices and then studying how they perform and also how stable they are. And we can do it all in this controlled environment. It's really a privilege.
I have to say, trying to get the microphone kit to you was the hardest I've ever had. It was the most secure space trying to get onto your floor. Like, badge never worked. No one would let me in. It was impressive. So you said your goal is to create not just high performing tech, but bankable tech, which is a term I love. But what makes something bankable, and why is that a benchmark that matters so much?
To me, there's a couple elements in bankability. So when we're thinking of the economics, and we often are doing more and more techno-economic analysis in our group, is that when we succeed, when we achieve the performance levels that we're targeting, can we be assured that we'll be able to make, let's say, a fuel or a material or electricity for a lower cost than the existing incumbent alternatives? The next element, and this is a place where Northwestern is absolutely at the frontier as well, is life cycle analysis. Like if we're thinking about the impacts on the environment of something that we're doing, we need to think about, are we producing carbon dioxide emissions in the course of making something? And how do those compare with the carbon dioxide emissions that we save through the lifetime's use of this product? And then the other key element, and it's all kind of connected in bankability, is that we can assure through a scientific understanding and through robust engineering testing, we can assure that the product will last those 25 years or 30 years, or for some consumer electronics, it's 10 or 15 years. So we need to be able to know with confidence and persuade others that the technology will be resilient over the projected life scale. And actually, that connects back even to the life cycle analysis. When you think of if there's some emissions associated with making it, you kind of amortize those over the lifetime of the product. And so you need that bankability to even think about the full life cycle and its net benefits.
You've talked quite a bit about the different collaborators at Northwestern. There's all this cross-disciplinary research that's happening. And one of your collaborators so happens to be your wife, Professor Shana Kelly, who is the first guest on this podcast. Do you mind talking a little bit about that? We always like to hear a little bit about these powerhouse couples we have here at Northwestern. Tell us what it's like working with her personally and professionally.
Yeah, it's been fun. We first got going, I guess it was even a little before we were married, doing some work on kind of basic nanomaterials chemistry. And she brought such tremendous expertise in kind of managing the interface of semiconductor nanoparticles and thinking about organic and even biomolecules that you could use at the surface of nanomaterials. And then we kind of moved together into some work on sensors. We do biosensors together. She really leads the charge, and I kind of help out, and my group helps out from a device and electrical engineering perspective. And then in the intervening period, we also did some work on catalysts together. That work that we were talking about, CO2 and upgrading it, she and her team brought this really deep expertise in nanomaterials growth and characterization that was critical to the success of that project.
And she spends a lot of time in Chicago these days too. Can you talk to me about do you get down to her offices in Chicago very often, or do you guys collaborate in Evanston?
We collaborate in Evanston. She's leading the Chan Zuckerberg BioHub Chicago, which is incredibly exciting and a huge and really impactful opportunity, and also really a transformative and visionary investment on the part of Chan and Zuckerberg. It's very exciting. A lot of Shayna's and my collaborations are really on the Evanston campus. And I tend to go to Chicago when I want really, really good food. And
That's right.
so
Well, they're in the West Loop. They have the best restaurant.
exactly. So yeah, we're
Yes.
our next dinner date is next week. We're going
Love
to
it.
a Michelin starred restaurant celebrating our anniversary. So that'll be fun.
Well, congrats. It doesn't get much better than that.
So obviously, the nano landscape, or nanoscape, if you will, is vast, and it's literally almost impossible to keep up with everything coming out, not just out of your lab, but Northwestern as a whole. So what future breakthroughs are you really just most excited about in next 5 or 10 years?
I think the biggest, most impactful thing that's going to happen is that I think we're going to understand even more deeply the relationship between when we synthesize a material. First of all, how does the synthetic process occur? Like, how do we really program how each atom ends up where we want it to? And then to understand exactly the functional relationship between how those atoms that are, say, presented on a surface and have a catalytic function, or they have an optoelectronic function, how that structure and composition, how that programs properties and performance. And then we're going to use all that to more quickly get to better devices, better solutions relevant to energy, climate, next generation electronics. And I think there's going to be elements of that that include the AI advances that we've been talking about today. But I think we also shouldn't forget about the critical importance of basic science. I mean, what I'm describing is a better basic understanding of how the world works at a kind of chemical, atomistic, materials, and molecular level. And while the field has progressed tremendously over recent decades, we've got much more work to do, and investing in that fundamental science remains as critical as it always has been.
So really, it sounds like the next generation of scientists have a lot of work to do, and You've mentored many young scientists. So, what do you think today's emerging researchers just really need to hear?
I think sticking to the plan is the right approach. I mean, this field has flourished on its recognition of the critical importance of advancing basic science, but you can do that kind of arm in arm with also striving to tackle a really important practical and applied problem. You can do it while building companies. You can do it while collaborating with companies. You can partner with national labs to try to have translational impact. And so I think this field of nanotechnology and nanoscience has been amongst those that has really pushed the frontiers of collaborative interdisciplinary work. And I think its continued success will be in part owing to its continued with that philosophy.
So, Nano Day is coming up in October. You actually wrote a book for like more of a lay audience about nanotechnology a number of years ago. So, if you had to pitch nanotech's biggest unsung hero to the public today, can you talk about that? What message would you send to the general public about the importance of nanoscience and nanotech?
I really see maybe the greatest success of nanoscience and nanotechnology is that so many people around the world are doing it and are actually not talking about it. And so, recognizing the fact that the nanoscale properties of surfaces and how atoms organize themselves at interfaces between two crystals, we recognize that that is incredibly important. It's actually just fully baked in now to curricula. It's baked into so many research problems in engineering and material science and in chemistry and in physics that we're often doing without talking about it. And so it's truly become pervasive.
Do you think people need to be talking about it more? Do you think the public needs to have a better education on, what's happening in these labs?
I think we do need to talk about our work more, and I think we need to communicate maybe first why we're so passionate about it, like why we're so excited about it, both from a curiosity perspective, but also from an applied perspective and the kind of impact we're trying to have. The students that work in our labs are so passionate about it from both of those perspectives. They're so deeply curious about understanding the world and advancing knowledge. And they're so deeply committed to some of these really mission oriented problems in medicine and in the energy sector and in enabling people to communicate and connect with each other. And so that passion and absolute conviction is one of the most exciting things about going to work every day.
Thank you, Professor Ted Sargent, for coming on the podcast today. This was fantastic.
Thank you.
Thanks so much for listening. This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Be sure to follow this show on Apple Podcasts or wherever you listen to podcasts, and be sure to give us a 5-star review.
For more information about IIN, go to our website, iinano.org/podcast.